Have you experienced this? In the daytime, your internet is as fast as it should be. But in the night when you want to play a game or having a video call, it slows down dramatically. Streams are buffering, your game is lagging, and your downloads are slowing down. At first, you may blame your Wi-Fi or complain to your internet provider, but most of the time the slowdown is not happening in your home. It's happening when your data leaves your home, especially when enough people are online at the same time. But you may ask why? To know the answer, you need to understand how the internet works. Your internet connection is not a direct line to a server. It's a route. Every time you load a video or open a website, your data is broken into packets, and those packets travel through a chain of networks, from your router to your internet provider, and then across multiple independent networks before reaching their destination. And each step in that path matters, because the internet is not a single system. It's a collection of thousands of separate networks, each owned by different companies, and they're connected to each other through agreements and shared infrastructure. Your data moves across this system one segment at a time, and at each segment, it depends on available capacity. At night, you are not just using the internet. You are competing with millions of other people. It doesn't matter if you are streaming a video, playing games, downloading updates, or synchronizing your data. You are competing with other people all at the same time. This creates the first problem: congestion. At key connection points between networks, traffic from many users converges. These links have fixed physical limits. When demand approaches that limit, routers start buffering incoming packets. Latency increases, queues build up, and once buffers fill, packets get dropped. At that point, the system starts reacting. For example, protocols like TCP detect packet loss and retransmit the data, but that adds even more traffic into an already congested network, which increases pressure further. So instead of stabilizing, the system enters a feedback loop. More traffic, more delay, more retransmissions, and again, even more traffic. But congestion alone doesn't explain everything, because not all traffic behaves the same way. Most popular content, especially video, is delivered through CDNs, or content delivery networks. Those systems store copies of content in many locations around the world. Instead of loading a video from a single distant server, you are usually connected to a nearby node. Under normal conditions, this makes things fast, but at night, those local CDN nodes can become overloaded. When that happens, your request is redirected, not because something is broken, but because the system is trying to balance load. Now your data might travel to a server that's further away. That means more distance, more network hops, more chances to encounter congestion along the path. So performance drops even though your connection hasn't changed. This is why you can see inconsistent behavior. One video loads instantly, another buffers. One server works perfectly, another struggles. Same device, same connection, but different path. And that path is not something you control. Routing decisions are made dynamically by the network itself. Protocols decide whether your traffic goes based on policies, cost, and availability, not necessarily real-time congestion. So even if a faster path exists, your data might not take it. There's another layer to this. Let's call this traffic shaping. When networks become saturated, providers do not just let congestion happen randomly. They actively manage it. Some types of traffic may be prioritized. Others may be slowed down. Heavy users might be limited temporarily, not as a failure, but as a way to keep the system stable under the load. Because without these controls, congestion would cascade much more aggressively. Entire sections of the network could become unusable. So instead of everything failing completely, performance is reduced across the board. Slower but stable. And this leads to the key misconception. People think internet speed is the property of their connection, but it is not. Your connection only defines the maximum speed between you and your internet provider. After that, your data enters a shared system with shared limits, even with a shared infrastructure and shared capacity. At night, those shared resources are under maximum pressure, and that's when the limits become visible. What you're experiencing is not randomness. It's the system behaving exactly as designed, balancing the load, managing the congestion, and keeping the network operational under the stress. But from your perspective, it feels like everything is slowing down, because in a way it is, and you're right. You're not being singled out, however. You are not just being throttled, you are competing. Competing for bandwidth at interconnects, competing for capacity in routers, and competing for access to shared links. And when demand exceeds what the system can handle, everybody slows down. The idea of shared limits under the load shows up everywhere. In CPUs where processors compete for execution time. In memory systems where bandwidth becomes the bottleneck. In GPUs where thousands of threads share the same hardware. In distributed systems where network links define performance limits. Internet is just one of the most visible examples because you experience it directly every time it slows down, especially at night. This is ML Guy, and together we try to understand the systems under the hood. Until the next video, good morning, good afternoon, and good evening. Bye.